Okay, on these last questions, at first they give you a force time graph right down here, and force on the y-axis, time on the x-axis, and it goes, force goes from 0 to 8 newtons in 4 seconds, and then it's this constant force for the next 4 seconds. And it says refer to the, or what is the impulse, refer to that graph, right? And what's the impulse on the object over the 8-second interval. For starters, if I ever give you, or if anybody ever gives you a force time graph, area is impulse. That's what you do with it. All right, find the area and find the area of the triangle plus the area of the rectangle in this case. Okay, area of the triangle, which is a half of 4 is 2 times 8 is 16 Newton seconds or kilogram meter per second. And then this is from 4 to 8 is 4 seconds. 4 times 8 is 32 Newton seconds. And so the impulse equals 16 plus 32 is 48 Newton seconds. Comes from the area of the graph. Then it says, what's the change in momentum of the object over the 8-second interval? Well, remember that impulse causes change in momentum. The reason why something changes its momentum, the reason why anything changes its motion, is because a force is applied over a period of time. All right. Now again, this is whatever that area is here is that equals that. So the answer's got to be 48. The change in momentum is equal to the impulse, and so the change in momentum is 48 Newton seconds or 48 kilogram meters per second. 48 kilogram meters per second. Delightful. If the, I find a typo in mine, I'll correct it by the time you get this. If the object starts from rest and has a mass of 2 kilograms, determine its velocity at 10 seconds. It's supposed to be 8 seconds. So determine its velocity at 8 seconds, at that point right there. So if it starts, what did I say? If it starts from rest and has a mass of 2 kilograms. So in the initial velocity is 0. Well, I just calculated that the change in momentum is 48. So delta, can you see this? Yeah. Delta P, which is 48, equals the mass times the change in velocity. Remember, change in anything is always final minus initial without exception. So this is 28, because, no, 48, bad teacher. 48, that's that. This is 2. And again, I get to use 48 because it's asking for it at the very end of the cycle, at the very end of the situation, which is at 8 seconds. And we know that from 0 to 8, the thing's 48. So the mass is 2. We're looking for VF, and it says it starts from rest. So divide 3 by 2, and then VF has to be, 24 meters per second. Be careful, because I might give you something where that's not 0. It might have some other initial velocity. Okay? Yay. That's that one. Oops, I don't have a rag to erase. Don't go away. Don't leave. Don't leave. Hi. Okay, it's going back down. Yeah. What's the next one? Oh, thanks for asking. So, cart A has twice the mass of cart B. They travel towards each other, collide, stick together, and stop as a result of the collision. So, this is A, and it has a mass of 2m, and here's B. It has a mass of m. We're going towards each other. And as a result of the collision, the final velocity is 0. They stick together. And they have the same, they're both 0, right? They travel towards each other, collide, stick together, stop as a result of. What can you say about the speed of cart A compared to that of cart B? Well, momentum's always conserved. And so PI equals PF for the whole system. And this is going to be the momentum of A, which is 2 Wait, A has twice the mass of B? Yeah. What can you say about the speed of cart A compared to that of A? It must be half the speed. I asked for speed, not velocity. So I know their signs are different. So this would be VA, and that's VB. And they have to add up to 0, right? So the momentum of A plus the momentum of B have to add up to 0. In other words, the two momentums must be equal and opposite. Okay? So let's change colors here. So the two momentums must be equal and opposite. So the momentum of A initially must be equal and opposite to the initial momentum of B because they have to add up to 0. So, and this is 2m because it has twice the mass, 2m times its initial velocity. And this one has only a mass of m times its initial velocity. You could just think this through. I mean, it makes sense that if this one has twice the mass, then it must have half the speed if they're going to collide and stick together so that the overall momentum in the end is 0. If the overall momentum in the end is 0, then the overall momentum in the beginning has to have 0. If you have twice the mass, you have to have half the velocity, half the speed, so that this momentum is the same number but opposite direction of that one, so they add up to 0. That makes sense. Mathematically, it works out like that. So that is half of that. Okay. How are we doing on time? Oh, okay, good. What can you say about the speed of cart A compared to the B? So it's half beforehand. Compare the change in momentum of cart A to the change in momentum of cart B. All right. Well, they must be equal and opposite. All right. That one. And that's always true, right? In a collision like this. So the change in momentum of A is equal and opposite to the change in momentum of B. They have different masses, and so they have different velocity changes. You could have done the previous question with that one too, right there. They're equal and opposite. What happens to the total momentum of the system as a result of the collision? What happens to the total momentum? Momentum's conserved. Nothing happens to it. All right? The momentum of the individual pieces change in an interaction like this, but nothing happens to the total momentum. Momentum's conserved. What happens to the mechanical energy of the system as a result of the collision? Well, remember that kinetic energy can never be 0 because you square the velocities, and so even if you had a negative velocity, you square it, it's positive. So you have cart A has positive kinetic energy. Cart B has a positive kinetic energy. And so the whole system has a positive kinetic energy before it collides. At the end, what's the kinetic energy at the end? It all comes to a stop. There's no kinetic energy in the end. So although momentum's conserved, is kinetic energy conserved, which is mechanical, because there's no potential energy change here. Is mechanical energy conserved? No. In fact, it's not only not conserved, it completely dissipates because it goes to 0. So the kinetic energy of the system initially, that's A and B, does not equal the kinetic energy in the end because that, my friends, is 0. Okay, and in the beginning it's not, again, because you can't have negative kinetic energies. You have the kinetic energy, which is the energy of its speed, plus the energy of its speed, which is not 0. So what happens to the mechanical energy of the system as the result of the collision? It not only goes down, it goes to 0. So is this an elastic collision? Oh, no. All right, it's a perfectly inelastic collision. Like it's the extreme of perfectly inelastic collisions because all the kinetic energy is lost. Okay, so on questions 49 through 51, carts have the same mass. Cart A is going towards cart B, which is at rest. And it says that they collide in a perfectly elastic collision. So both momentum and kinetic energy are conserved. Compare the change in momentum of the two carts. Well, it's always going to be equal and opposite, no matter what. Inelastic, elastic, whatever kind of collision it is. they'll always be equal and opposite. The change in momentum of A is equal and opposite to the change in momentum of B. In terms of the velocities of the car, if you think about like when you're playing pool and you hit the cue ball, if you ever play billiards, you hit the cue ball strikes a stationary ball head on, the cue ball stops while the other ball leaves. That's because they have the same mass, and it's close to a perfectly elastic collision. Not completely, but it's close. So that would be a situation where afterwards this one would come to a stop and that one would leave. They exchange velocities. Since this is true right here, so m delta v a is equal to m, because they have the same mass, negative m delta v b, the m's cancel. So the change in velocity of A is equal and opposite to the change in velocity of B. In other words, they have the same change. If that one comes to a stop, that one starts and takes off. That's what that means. And then the last question on these momentum questions is, what's the change in mechanical energy of the entire two-cart system over the collision? The answer is there isn't any change, right? It's a horizontal, frictionless environment, perfectly elastic collision in which kinetic energy of the system before equals the kinetic energy of the system afterwards. And you can see that here because 1/2 times the mass times its velocity squared is a number. That one's 0 before the collision. And then after the collision, this one's 0, and that one with the same mass has the same velocity that one used to have. 1/2 mass times its velocity squared. The kinetic energy before equals the kinetic energy afterwards. It is conserved, as you know, in an elastic collision. All right. So those questions on the review sheet where you have to sketch the kinematic graphs, I know that so many of you love these things. Anyhow, the position time graph is given. And this object starts at some positive position. I'm looking at the brown one. Starts at the positive position. Notice it has a negative slope. The slope represents velocity. And it's a negative slope, and so it's a negative velocity. Negative velocity is down here below zero velocity. Zero velocity goes along here, so it's going to be down here somewhere. And remember that the steepness of the line, try to do that, and the steepness of the line represents how fast it's going. It starts out really, really fast because it's really steep. And then it gets shallower and shallower. It levels off, and the slope of level is 0. It's flat. Means stopped, right? Stopped is anywhere on a velocity graph right along this line. So it starts out negative, and then it ends up stopped, and there you go. Negative velocity, the object is slowing down in the negative direction. Slowing down in the negative direction. That's a positive slope. That always throws people for a loop. That's a positive slope right here. And remember, the slope of a velocity time graph is the rate of change of velocity, not the rate of change of position, the rate of change of velocity. And even though this thing's moving in the negative direction, it has positive acceleration, which is a positive rate of change of velocity. So that would be a constant positive. This comes from that slope. A constant positive slope gives me a constant positive acceleration. Over here, here's another object that's slowing down, all right, because it starts out steep but with a positive slope. So it's positive velocity, which is up here somewhere. But then it shallows out, and then right here it looks like it's just flat, which is standing still at some positive position. So starts off with a positive slope here, so that's going to be up here somewhere. And then it stops at that point. So it's moving positively, but coming to a stop. And stop is anywhere on the time axis. Okay? And it stopped there. So that's a negative slope right here. So you have a negative change in acceleration, negative change in acceleration, and then no acceleration, the last part. Well, that was fun.